All right, we are back, everybody. Welcome to the stream. I hope everyone's having a wonderful day so far. Let me go ahead and actually pull up the PDF. I have lost it here. Here we go. All right, and let's go down to our place here. All right, I hope everyone's having a wonderful night. Sorry I'm a little bit late. I was rendering out a video for the channel, so I have an excuse. I was working on the channel. Don't bite my head off. But yeah, that was I just released a demo video for the task tracker project that we built live on stream. So if you're interested in seeing a demo of that project, please click below and in the description, or not in the description, in just the channel, and you can see the most recent upload for the demo. Hello, Kerwin. Thanks so much for joining me. I appreciate you. Present. Check. You are here. Welcome. It's good to hear from you again. Awesome, Kerwin. I appreciate you joining in. Thank you so much for letting it play. That's so nice of you. Thank you. All right. All right, we are on 32 here, I believe, of the DSA. We are going to work on data structures and algorithms in Python. We're going to finish up the last 3 problems of this chapter, and then we can dive in and do a little, maybe read the first couple of pages of chapter 4. So we are going to really be taking off here and getting into the thick of the book. So you heard it here first, folks. Be here for that. Okay, let me clean off my keyboard here. Got a hair on it. Get out of there. There we go. This is going to be R 3.32 underscore key.py. So go ahead and throw that bad boy in there. Let's go ahead and make this. And then take this guy, copy it over. Boom. Playing in the background. Scoopa Doopa Dolphin. I appreciate you coming. Nice name. That's such a cool. I like your name. Scuba Doopa Dolphin. Scoopa Doopa Dolphin. Oh no, Scoopa the Dolphin. The Scoopa Doopa. That's funny. All right. Thank you for joining the stream and leaving a message. What brings you in this evening? Hopefully, it's still learning some Python here. Let me just, I'll just pre-make these files. All right, 1, 2, 3. We'll take this guy, bring it over, paste it into here. Take this guy, R 3.34 underscore key.py. Go in here, 1, 2, 3. Then bring this guy over. All right, we got some people in here. Welcome back, everybody. We got some regulars back. We got some new people. So I am super excited to welcome everybody in today. We got Avanaj. Hey, how's it going? How you doing today? We got Naj. Yo, welcome. Scoopa says, I'm a first-year undergrad student in CS, so seeing this is really, really cool. Awesome. I really, that's super. Thank you so much for the feedback. I'm so glad that you found we were able to connect and network here. Welcome to the channel, and let's learn together some Python and some computer programming. And, it's going to be interesting. I actually enjoy that you shared that with me because I want to maybe pick your brain a little bit throughout the stream or in the future on your, what you're learning so far as CS as a freshman, because I'm considering maybe if the market clears up for people with computer science degrees, not necessarily that you have to have a degree or anything like that, but I might consider going back and getting a post back, and because I already have a Bachelor of Science in Human Biology and a minor in Chemistry, but I am considering, I was at least going back and getting that CS degree as well. It would only take me about 2 years at my alma mater. I think that's how you pronounce it. But yeah. anyways, that's just a consideration I was thinking about, but nothing too crazy right now on the moment. So thank you so much for joining. Jeremy, welcome. Appreciate you coming into the stream today and joining me as usual. Welcome, friend. Scary Sticks, is that a good book? Welcome, Scary Sticks. I appreciate you joining the stream and leaving a message. Yeah, so we're reading Data Structures and Algorithms in Python. We have read so far we have read on stream live all of Python Crash Course, where we dove through and really solidified the beginner concepts of Python as a whole, and then we actually implemented those into a project. I recently just posted today, actually, the demo video for the Task Tracker project that we completed live on stream together. It's just a short little demo to, showcase that. So feel free to check that out. Right now, we're doing data structures and algorithms in Python. We are at the end of chapter 3. We got 3 more problems, 32, 33, and 34, and then we're going to move on to chapter 4 and start diving into some new material. I do the reinforcement problems at the end of the chapter, and I keep a running notes. And this is on my GitHub and everything. Whew, running out of breath here. Hold on, where was I? Lost my train of thought. Yeah, so then after we get through DSA, we're going to go through Fluent Python. Big thick boy here. And then we are going to do Python machine learning shortly after, or we might intertwine these as we want to get new subject matter. And but right now we're doing DSA, so we're going to get pretty deep into this book before we maybe start transitioning into other material. But yeah, thanks so much for joining. Before you lock back in, what made you want to learn data structures? Yeah, so actually quickly, like I said, I have a Bachelor of Science in Human Biology and a minor in Chemistry, and I work as a formulation chemist for a biotech company where I make biological controls used in patient diagnostics. Basically, kind of fancy terminology for I make kind of testing materials used to diagnose patients, like what you would run to compare results again for various ranges of diseases, or like blood levels and things like that for diseases. So, or like serum levels, or cerebral spinal fluid, things like that. Um, I have a lot of instances at my work where I have to hand calculate, chemical matrices and predict theoretical concentrations of large products. And I have to be fairly accurate, for good results, to make the company money at the end of the day. And so there is a lot of pressure at the end of the day to do this correctly, because in chemistry, it's pretty hard to go backwards once you've gone forwards. Um, anyways, that sparked the interest of, oh my gosh, I wonder if a computer could do this for me. So I quickly, researched into, languages and computer science. I bought a laptop. Had a desktop, but I bought a laptop to have mobile and make it more mobile, and started the channel. And then I started Python CS50P offered by Harvard online. I completed that very part time over the course of this past summer of 2024, and then I, completed a final project in that class, and that's what really sparked the, oh wow, I can make something from nothing with this. I don't have to go outside and play with hammers and nails and be in the cold. I can sit in my desk and stream and make cool things. So, and it's just limited to your own creativity and your own willingness to learn, really, in my opinion. So, um, yeah, if that's something that sounds interesting to you, we are growing the channel quite rapidly. We're almost at 400. I'm like I don't know if it's mirrored or not, but 400 subscribers, which is just mind blowing that we've accumulated such an audience here on the stream, and I appreciate all the support and love I've been getting. It's been very very helpful in getting me to come and do these streams. Knowing that I have you guys to come talk to on a daily basis. So for all those people that tune in day after day, and even for those new people today, thank you so much for joining. I'm glad we can become friends and acquaintances. But yeah, so again, I like to just, because I already have a job, and I often have seen from an outside perspective, the CS market is fairly competitive and oftentimes quite cutthroat. So this kind of environment kind of can take that away. We are friends, we are peers, you and me, as if we were in class together studying this. We're in a library room studying this we booked, right? We're together in this, just like we were back in school, or if you're in school, right? So that's the whole purpose of this. And, just to take this at our own pace. Rome wasn't built in a day, as they always say, so why should we force ourselves to try to learn this in one day? Okay. All right, let's go ahead and give this problem a shot. That's enough rambling for the intro. I've been going for 10 minutes here so far. So, anyways, let's get into the actual uh, stuff here. We only have three problems, like I said, and then we're moving on to chapter four. And I do read the chapters out loud. Like I read them out loud. I break them down. If I don't understand them, I break them down with AI to even further, and I don't move on unless I really kind of get it, because if I move on without understanding it, it only hurts me and it only hurts you guys. So we're going to understand this stuff whether we like it or not. Okay, so let's catch our breath here. Rambling over here. All right. There is a well-known city, which will go nameless, whose inhabitants have the reputation of enjoying a meal only if that meal is the best they've ever experienced in their life. Otherwise, they hate it. Assuming the meal quality is distributed uniformly across a person's life, describe their expected number of of this city. Describe the expected number of times inhabitants of this city are happy with their meals. So, which is really interesting. This is actually a cool theoretical problem, because if you think about this, it's saying that for every meal that they take in the form of n, right? So the function in this case is the person, right? And it's processing some food. So f of n, and n is going to be equal to some food, right? N is what the person's intaking, so it's going to be that meal. Now, think of this as a list, right? Where we have some values, and so we have a meal here, meal one, then we have meal two, and then we have meal three, right? And so on and so forth. Now, the user only gets enjoyment if their next meal was the next greatest meal they've ever had. So what this is saying, this is the same exact problem as I think our find max function, right? All we are doing is comparing the um, the meal so right, if they start on this one, this becomes the best meal they've ever had because it's the first meal they've ever had, and technically in this series. Now they go on to the second one. We compare it to the first one. It wasn't as good. Let's move on. Oh, meal three, best one I've ever had. So this function is the same as the biggest or the find max function, which I believe, did we not diagnose back here? I think we tried to, but we accidentally diagnosed the example one function, or on accident. Um, so in this case, function of n would equal big O of, you loop through, you do a check, you override. So I believe this is going to be a big O of n time complexity. Now I say that because, did I do 30? Oh, whoops. I started on 34 over here. Whoops. We're going backwards here. Um, got some chats here. Hold on. Let's get caught up on the chats. Jeremy says he likes to torture himself nightly after formulating chemicals all day. Exactly. I was thinking of reading the Scanna's book about DSA, but maybe it's too theoretical. This book, I mean, I think you don't. I think you might be scared of just making the leap. I think all of these concepts are going to be theoretical in some way or another. Just because you're dealing with math, right? You're dealing with application, applying that math to functions. Um, so you have to be able to think about it in that way. So I think any book that's going to go over this is going to probably present it in a theoretical way, but hopefully they provide you examples to make that more clear. So, right, if we think about this, we go, so for meal in meals, if meal is greater than we assign meal to biggest or greatest, the best meal, and then we iterate through for meal in meals. If meal is greater than meal or best meal or greatest meal, then override, right? So, and then return meal at the end. So this would be just O of n time. Yeah. Anybody have any disagreements with this or agreements? What do we think? Let's go ahead and uh, a find max function is big O of n, right? Yes, a find max function iterates to all elements where, and so, okay, cool. So I believe that this is correct. So this is similar in structure to the find max example used in the book. Quote, distributed uniformly. I agree, it's linear. Okay, so there is a whose inhabitants have a reputation of enjoying a meal. Um, yeah, so right when we learned about I'm gonna go to that find max function to show you guys here for those that are new today. So we get a max. Sorry. Where are you? Where are you? There we go. So all this is doing is this problem is making the same example as our find max function here. But it's just saying it in words. So we are given some list of meals or inputs n in this case, but for this example we're meal 1, meal 2, meal 3, yada yada yada. And then we would assign the favorite or best meal, but in this case for the find max, the biggest to the meals, right? I'll make it this actually like, right? So we assign the first one to the biggest because if we've never had food before by this problem, and we have a meal, and we go to the city and we have a meal, then that meal is the best meal we've had in this city, technically speaking. So because we have nothing else to compare it to. So then when we go have our second meal, we will then compare it to the first meal. If it is better, we will override this biggest or favorite meal variable, for the value or the meal that we're iterating over currently, right? And then at the end of that, we'll just return the best meal that we've ever had and say, okay, well, meal 2 was actually the best meal we've ever had because that's when we returned, right? So this is the exact same as this function in theory. Harry, thanks so much for leaving a comment and joining. I appreciate you. Says, hey, Michael, quick question. Is this your full-time work or are you working part-time and then working on this on the side? Sorry, I work full-time and I do this after work. Yeah, so I am very busy in terms of just time. I I don't, streaming, I get to, this is something I enjoy, so it's not work. Like, this is a hobby of mine, and I stream it, stream my hobby, and it just makes it even better. But I do work a 9 to 5 as a formulation chemist. I have a bachelor's of science in human biology and minor in chemistry. I graduated back in 2021, and then shortly, just pretty much right after I graduated, I got a job as a formulation chemist for a biotech company, and I've been there ever since. I'm now a mid-level chemist in that company. And so yeah, after my 9 to 5, I come stream every day from about 7 to 9. At least I have been for the past over a week now, and almost 2 weeks, I bet. And then I'll occasionally upload videos to my channel of just recapping and summarizing, my learnings and things like that we do on the stream. So yeah, thanks so much for jumping in here, and I appreciate you coming in and following along. I look forward to hearing more from you. All right. Glad to be here. It's awesome seeing you. Awesome. Thank you so much for the kind words. Okay, let's go ahead and we started off with 34, so let's just back down to 33 here. Okay, Al and Bob are arguing about their algorithms. Al claims his O of n log n time method is always faster than Bob's O of n squared method. To settle this issue, they perform a set of experiments. So we know just by our definitions of our functions that an n log n function is going to be faster than a n squared or a quadratic function. So Al thinks that in all circumstances, but if we have a large enough constant for a small enough n, we might have cases where that might not be true. But let's think about this. To settle the issue, they perform a set of experiments. To Al's dismay, they find that if n is less than 100, the O of n squared time algorithm runs faster. Exactly, for small n values, just like we had just predicted. See, we're getting this, guys. We're getting this. We are getting this. The O of n squared time complexity runs faster. And only when n is greater than or equal to 100 is the O of n log order. How do you explain this, right? So this is just like a theoretical. So when determining time complexity of functions slash algorithms in this case, we are specifically targeting very large input values, so x, so n goes to infinity, when defining, so for determining, when defining big O, right? So, and this just basically proved that. So big O is technically irrelevant, right? For small inputs, because a computer is generically going to run very, very fast for small inputs, and depending on your algorithm, that'll just vary slightly. But you could have, right, these inputs or these slower functions run very fast for small inputs, because we know, right, that a small input value of 1 to the power of 2 is just 1 compared to log n of 1 times log n of 1, or n, what would that be? Let's pull up, sorry, I'm stuttering over here. Let's pull up Safari here, and let's do Desmos. And then let's look up, what's 1 times log 1? 0. So you can't even do log 1, so, but we need log base 2 here, so that's still 0. So then what if we put a 2 here? This should be 1. No, this is 2. Okay, and then what if we do 3? 3, and then do 3 to the power of 2. Interesting. So that for n values less than 100, the O of n runs faster for values. So when determining time complexities, f of n is equal to n log base 2 of n L2 of n, oh whoops, squared. Okay. So based on this, let's make this a little bigger. Oops. Right, based on our graphs here, for small input values, our n log n function, our n squared function runs faster. So if we say x is equal to 3, am I missing something here? So when we have an x equal to 3, 3 and 9, 3 and 4.75. So our n log n is faster here, even though the problem says it's not. Um, we got some chats here. Sorry. Dat Kid Dude, thanks so much for joining. He says, what's your background with mathematics? This chapter was so hard for me for understanding, even watching videos on how to prove big O. Um, yeah, I do a lot of mathematics, not complex mathematics, but just kind of conversions and basic, a lot of conversions with chemistry and things like that. So I do use math on a day-to-day basis, just basic math and functions and things like that. But I haven't done math like this since honestly, my freshman and my junior year of college. My freshman year of college, I took calculus, and then my junior year of college, I took statistics for science, and so that was all about like normal curves, p-values, alpha values, everything, all that kind of stuff. So I don't remember a lot from that, to be honest. But yeah, it's been a while. So, don't feel discouraged. I don't have a super strong foundation in math. I just have, the general education system and whatever outside I put into it. But let me move over my light here. Yeah, so just take it at your own pace, and really, it's not, um, it's just try your best to sort it out. I guess that's what I'm saying. Um, Definitely, just watching videos afterwards helped. Doing these graphs, seeing it visually helps as well. So if we have an x equals 1 value, our n log n function cannot even perform this, right? Oh my gosh, come on. Right, this runs in 0 time. This can't even perform this function. Whereas we can get a value here. An algorithm is bound by O of log n. Roland Owner says, hey dude, are you studying for a software engineering position? No, I'm just studying independently to further increase my skills and my knowledge in general. I think it's crucial to continue your education in any ways possible. So I just have found that I really enjoy computer science and programming. So this is a by means of doing that. So they claim though that for every, so if I do, how is this function running faster for lower inputs less than 100? So if I put 99 here, and I do 99 times 99, and I just get rid of these and just give me the math of it, this function is way faster than this function, right? For an n value less than 100. Oh, these are for their specific functions. Oh, okay. So, right, they're not saying that their function is n log n. It's time bound, upper time bound is O n log n. So, in its worst case scenario, it will run in n log n. So, it's just their specific function with when applied to these. Okay. big O is worst case, so the math they may be just exploring the idea of x squared not running worst case. I guess that wouldn't make sense if they are big O notation. Yeah, I think they're just trying to show that they have some arbitrary algorithms that are bound by these, right? They're bound, and so just trying to hone in that general idea of we don't care about um, the small n values. The situation described illustrates an important constant factors and lower order terms in real world algorithm performance, especially for smaller input sizes. Big O focuses on asymptotic behavior. Big O notation describes the growth rate of an algorithm's running time as the input size n approaches infinity. It ignores constants and lower order terms because for very large n they become negligible compared to the dominant term. Small n in real world performance. For small input sizes, constants and lower order terms can significantly affect the actual running time. That's exactly as well. So also for n values less than 100, constants and other what is it, factors or multiples? Constants and lower order terms can significantly affect running times. Other lower order terms can impact running, can significantly impact run times. If Al has constants or other factors in his algorithm, it may perform slower than Bob for n values less than 100. Perfect. Cool. That is the answer to that one. All right, moving on to 3.32. All right. So this one says, given an n element sequence, so we have a sequence which has, n elements in it, right? So we have given a sequence of n elements. Algorithm D calls algorithm E on each element at index Si. Okay, so we're saying algorithm D calls another function, algorithm E, on each element for some index of sequence, right? Algorithm E runs in constant time when it's called on element Si. What is the worst case running time? Okay, so I think this is trying to trick you by trying to make you think that this is a recursive problem when it's not calling algorithm D back on itself. It's calling algorithm E, an arbitrary algorithm that has a constant running time. At least this is what I think constant, right? Is this constant running time O of I? Some integer? Or is O of I in reference to this index value here? What do you guys think? Is O of I constant time, or is O of I referencing this index I variable? So algorithm D would just say for every element in the length in the range length of S, element S, element at index I would think linear. Okay. So then if that's the case, if it calls a linear function on a, you know, an indexing, so this is, I think this is just O of n. I think this is just O of n because, right, algorithm D will iterate through every element in the sequence, right? And then we populate that element. So we say for element in S, element at index I. No, we would say like this. We like for um, index in the range of the length of S. Um, we would go um, S at index. We would call right here algo D right here, right? And algo D, oops, has constant time. So this would just be big O for this one. All right, just be linear time, I think. What do you guys think? Do we agree? Do we disagree? Any other thoughts? Tarzan is live. I appreciate you coming in. I like your name. It says Big O of N is the first entire term of DSA in college. I just finished my course in CS. This gets easy if you write in paper and look at loops and try to solve. Recursion problem is freaking hard too. Feed, I appreciate you coming in. Thank you so much. Welcome back. Do we agree on this one, guys? We are calling a function, so not recursing. We're not having recursion happen because we're not calling algorithm D, right? So this would be like, this would say def algo oh, I'm sorry, I have this algo D is here like this. This should say algo E. Algo E as constant time. This is what it would look like. So then something algo E would look something like this. Would take in some value. And then say it would be like value times 2, right? Return value times 2. All right, so this is what's happening here is we have let's say we have 0, 1, 2, 3, 4, right? So we have some sequence of n elements. Sorry, some sequence of n elements given n element sequence S, right? This is our n element sequence S. N just represents the number or the physical. So if we called length of sequence, it would give us 1, 2, 3, 4, 5 in return, right? So We are then told we have algorithm D, which calls algorithm E. So let's first focus on algorithm D, and it does what? So it does something to each element at the sequence index. So what algorithm D does, it would say for index in the range length of S. Now what this does, if you think, right? So the length of the sequence is 5, right? From 5 integers, 0, 1, 2, 3, 4. 5 is our length of our sequence. Range would be 0 to 5. So we established a range of our sequence so we can, you know, establish that index variable. I have it actually representing the physical index here of 0, 1, 2, 3, 4, 5, 1, 2, 3, 4. But what if it was like 10, 12, 14, 18, right? Then it would not represent the individual index spots, but it rather represent those values. So we call range length of sequence to go from 0 up to the length of the sequence. And so then all we do is we access, like it says, S at that index. So we access the sequence S at that index, right? So if you, I will try to explain this. So we're going to first start at 0. We're going to, um, I'm sorry, we're going to first start at this position, the 0 index. We want to know if what index value, and we want to save that index value of this first position. Well, we know it's 0, but we need the computer to know it's 0. So the range length of S will start from 0 to 5. So it'll look just like our sequence here by nature. So our index value will actually resemble 0 for the first iteration. It'll resemble 1 for the second iteration, 2 for the third, 3 for the fourth, and 4th for the fifth, right? Because our lists are 0 indexed. Now I'll go ahead and I'll make this a little bit more clear in case that doesn't make sense. I'll make this like, let's make this 10, let's make this 12, let's make this 14, let's make this 16, and let's make this 18, right? So I'm going to come up here and make a comment and call the index, or I, for lack of better terminology, because I can't fit it. So 0, 1, 2, 3, and 4, right? So we're going to be accessing these values, not the list, right? Because we're creating this range length of the sequence. We're not accessing for value in the sequence. We're creating our own, like, creative way of saving the index values, and then we can access those sequences, in those values individually. So what this does is we essentially don't know ahead of time is how big the sequence is. So we have to call the range on the length of the sequence to gather the entire length. If we had a predetermined and already knew that every time that the sequence was going to be 5, we could just call, this sequence 1, sequence 2, sequence 3, sequence 4, and sequence 5. Because we would know that we could just call those individually 5 times because we know every time it's going to be 5. But if our list goes on all the way to n approaches infinity, well, we need to have O, 0, all the way to infinity for the range length of S. That would be what it is, right? So it's just a way of establishing that index. I really took me a while, like almost a whole week, to think about this and kind of understand what was going on under the hood. But now I'm feeling really comfortable about like saving the index value of a sequence of an unknown length, right? Which is this function set up here. So sorry, that's kind of off. Now we can get back on tangent here. Is that we then call algo E on that S of index, right? Sequence of that index value. And all algo E does is run in some constant time. So we just call a simple multiplication function to call on it. So I believe that this will run in O of n time. Oh, what is the worst case running time in algorithm D? Yeah, just O of n time. So we'll say algo underscore D is equal to big O of n linear time. Let's paste that in and see what they say. Uh-oh. Okay, so we read this problem wrong. So this, like we were saying earlier, is that O of I does not mean constant time. O of I means time at that index. Mm. So this will run in also linear time as well, I believe. So this, no, this does not, we can't say that. That's not that function. Has O of I time complexity. So then algo E has O of I. So index would be some value in the sequence. So algo E would have O of like 16, which would just be constant time, no? Or would it have like N plus N plus N plus N all the way to the third place? Or fourth place, sorry, the fourth index. So if this index is 4, does this mean you have N plus N plus N plus N? So this would be an N squared time, I think, where I is the index element being processed. Okay, outer loop. Algo D iterates through all n elements in the sequence, meaning there are n calls to algorithm E. Okay, inner loop, inner call, algo E. The cost of each call depends on the index. So O of, okay, constant time. Yeah, n squared. We're right here. Yeah, so although you're running a constant operation, technically speaking, with just a single value, this value is not just a single integer value, it's an index value of a sequence. So in order to access that, algo E, the cost of each call to algo E depends on the index I. For a sequence at index 0, the algorithm E runs in O of 0 time, 1 and 2. All the way for n minus 1, algo E runs in O of n minus 1 time. So sequence of 3, 2, yeah. The total running time of D is the sum of the two time complexity for the call. Interesting. All right. Yeah, so if this had a just a not an O of I, but just an O of 1 time complexity, then we'd have O of n for the total algo D. But because this has O of I time complexity, we are, indexing, and actually indexing itself is a constant operation, but when we are, it looks like it when we are within a for loop here, let's ask it, can you break down why algo E when called will run a constant O C. No, it's not O of C though, it's O of index. So let's ask it then how I am not understanding how O of C is different no, so we'll say O of I in this case is different from O of some constant. Yes, respond. Understanding the distinction between O of I and O of C is... Oh, no, I now understand. No, whoops, we'll say I am not understanding it. Sorry. No worries. Let's slow down and break it down step by step. So constant time, we already know that. O of I time, linear time with respect to I, what it means is the operation's runtime depends on the index I. If the I is larger, the operation takes longer. Imagine stacking books one by one on a shelf. To reach the fourth book, you stack 4 books. To reach the 100th book, you stack 100 books. The time it takes to grow as I grows. In programming, an algorithm takes I steps to process the ith element, summing up from 1 is O of I. So algorithm it doesn't always run in constant time. Instead, it takes longer depending on the index of the element it's working on. So algorithm D calls E for each element in the sequence. Yeah, because you're not accessing a constant value. You're not saying, oh, right? You're not just saying algorithm E isn't accessing 10, right? It's having a time operation of an index of O of I, which is in reference to algo D, right? So that's why we get that n squared, which is interesting to think about. Yesterday we solved this problem 331. No. This one. This one, Theed, I think, asked about this problem. Yeah, we solved this problem yesterday. This one was really hard. It took us a while to figure out what it was kind of asking because it did a conversion from log base 2 to log base 10 without telling us or telling us really how to do it either. So shame on the authors of the book for that, but yeah. My dog is snoring over there. All right. Naaman says, how are you doing, Michael? How was your day? I was really good. Thanks so much for asking. I've been starting a recent, no, not new, but a project that I've built quite frequently when it comes into the schedule. And I just recently started it up today. So getting back to the grind and the projects at work here. So yeah, projects at home and projects at work. What do we know? Okay, so let's go down here and I think that's it, right? Yeah, 331, 334. Okay, cool. I think that is it. What is going on with my mouse? Come on, just click on the file. Thank you. I'm going to make all of this just a comment. You staff, I appreciate you coming in. Just joining. What are you guys working on? We are working on the data structures and algorithms in Python book right now. We're literally just finished chapter 3, practice problems. We did 34 of them, if you guys can believe that. 34 practice problems at the end of this chapter. So we got a lot of hands-on experience with this chapter. And so we're going to move on now to the chapter 4. I'm excited here. Chapter 4. By the end of this chapter, we'll be on page 180. Cool. So this gets into illustrative examples, binary search, file systems, recursive algorithms, linear recursion, binary, and multiple recursion. So we're going to get deep into it here, you guys. Appreciate you joining, Yustaf, and leaving a message, though. And following along. Thank you so much. Let's go ahead and let's just push this up. will say finished chapter 3 reinforcement limbs. All right, we'll push that up. If you guys want access to all of these solutions and my live notes for chapter 3 and going on forward, feel free to download this from the GitHub. Are you good at calculating time complexity for complex algorithms? Well, we hopefully will get there. We are only on chapter 3 here, so we were given some beginner examples, or not beginner, but just introductory examples. So hopefully we can get better at explaining more advanced ones as we see them. But we only have learned about a few small examples. We haven't even really gotten to recursion and stuff yet. So we need to go dig further here, you guys. Okay. Let's see here. Now I know there was a request moving forward to write my notes. SSLORL says, "Is this the university's course or your own study?" This is completely independent. I have no motivation to finish this besides my own dedication and obviously wanting to finish this with you guys, because I've started this with you guys and I want you guys to hold me accountable to completing it. And so, we like to prove that we can do hard things ourselves, and this is a way we can do it. So, and you guys can do hard things too. So, stick with the channel here day after day, little by little. We'll understand this together, and we'll become better programmers together here. So we were asked to write our notes going forward in Markdown. So I think that's a good idea. So let's go ahead and do that moving forward. Chapter 4. Okay, we'll open this guy up. We will go chapter 4 notes.md. Cool. Yustaf Patel says, I mean, how important is it really? From what I understand, I'm not going to be going through any job interviews regarding this stuff. People go to 4-year degrees. I have a degree in human biology and in chemistry, but people have their specialties in this stuff and are having difficulties finding work. So again, that's another. This is independent and self-studying, so it takes that pressure out of it. I already have work, and so it's just more of a fun hobby thing that we are working on here. But if it leads to anything in the future, that's fantastic. But from my understanding is that almost every interview regarding software development, computer science, in some way will ask you a algorithm-based problem. It's just kind of the standard nowadays. Now, which one they ask you, whether it be hard or complex or hard or easy, that's just for the odds you get, I guess, right? So, but I've yet to hear from people that they are kind of stopping this kind of current way of doing things. So ASCII says, every day your YouTube suggests your channel to me, and I can see you're making progress on your studies. Very proud of your dedication. Best from Brazil. Thank you so much. I'm really happy that YouTube is getting me to the right people. And I appreciate you guys, participating and leaving me such positive comments and messages. You guys are too kind. Thank you so much. All right, guys. Jordan Woods, thanks so much for joining. It's good to hear from you again. Appreciate you. Okay, let's ask the Gypity. Give me a markdown summary quickly, or formatting guidelines. Here's a concise markdown summary. Understanding. No, stop. No, not for the just for markdown format as a whole. Okay, headings, use hashtags for headings. So you have, like you have bigger headings. You can use for lists. So use dashes or ASCII or stars for lists or numbers. Bold gets the stars. Code blocks, inline code, code block. Inline text, images, block quotes, tables. Okay, let's try this out. Chapter 4. Uh, recursion, right? Okay, so we're gonna have 4.1 illustrative examples. Uh, Gustav says, "True that." You guys are so kind. Theed, same thing. I'm from Brazil. Awesome. I appreciate. Well, that's really great that we're getting some international exposure here. Hello. I appreciate you guys joining. Markdown is very similar to Discord formatting. Okay. All right. So let's move on here. All right. Let's jump into chapter 4. One way to describe repetition within a computer's program is the use of loops, such as Python's while loop and for loop constructs described in 1.4.2. An entirely different way to achieve repetition is through a process known as recursion. Recursion is a technique by which a function makes one or more calls to itself during an execution, or by which data structure relies upon smaller instances of the very same type of structure it represents. Okay. There are many examples of recursion in art and nature. For example, fractal patterns are naturally recursive. A physical example of recursion used in arts is in the Russian Matryoshka dolls. Each doll is either made of solid wood or is hollow and contains another. So these are the Russian dolls. Yeah, got you. In competing in computing, recursion provides an elegant and powerful alternative for performing repetitive tasks. In fact, a few programming languages, Scheme, Smalltalk, do not explicitly support looping constructs and instead rely directly on recursion to express repetition. Interesting. Most modern programming languages support functional recursion using the identical mechanism that is used to support traditional forms of function calls. When one invocation of the function makes a recursive call, the invocation is suspended until the recursive call completes. Recursion is an important technique in the study of data structures and algorithms. We will use it prominently in several later chapters in this book, most notably chapters 8 and 12. In this chapter, we begin with the following 4 illustrative examples of the use of recursion, providing a Python implementation for each. In this chapter, we begin with the following 4 illustrative examples of recursion. Okay, cool. So, Markdown guide. So can we? What should we do for like? Can we do bullets or numbers? Okay, so let's just do this. Let's just do. We'll go like this and say. Um, Definitions. I'm going to take this guy actually and put it here up above for all definitions that we get. And we'll say, we'll make a list starting off. Okay, so let's first go back up and define recursion. Recursion is a technique by which a function makes one or more calls to itself during execution, or by which a data structure relies upon similar instances, a structure and its representation. Okay, we'll copy that directly over. Boom. Just like so. So we'll say this is right? Boom. Then we got there are many examples of recursion in art and nature, or fractal patterns, Russian dolls, um, recursion. Okay, cool. So 4 illustrative examples. So number 1, you have factorial function, commonly is noted as n exclamation mark, is a classic mathematical function that has a natural recursive definition. We have 2 is the English ruler. Has a recursive pattern that is a simple example of a fractal in nature structure. Oh yeah, so these are just visual or illustrative examples found, that we see. So we have a factorial function in math is recursive. Right? English ruler, recursive pattern. Binary search is among the most important computer algorithms. It allows us to efficiently locate a desired value in a dataset with upwards of billions of entries. So 3 would be binary search. And 4 would be file system. I'm just going to copy these definitions in here for the sake of just having some formal definitions. I like these as a recursive pattern and structure. I like that. Binary search is among one of the most important computer algorithms, allows us to efficiently locate put that right there. Boom. Gotcha. And then file system. Would be for the file system for a computer has a recursive structure in which directories can be nested arbitrarily deep within other directories. Let's take from here forward like that. Boom. Cool. All right. Hashtag is header. Oh, hashtag is header. Oh, shoot. That's right. My fault, guys. Hashtag is header. So this will be 3 hashtags for definitions. This will be 2 hashtags. And so then we will bold this guy. Right, like that. I like this. This is definitely cleaner than the TXT, right? And this helps kind of probably make things a little more readable for you guys as well. So I'm going to take this and go boom, boom, like so. Like that. You can toggle Markdown view with Command Shift V. Command Shift V. Oh, look at that. Okay, so what's up with my headers here? Oh, it's because I had something. Oh, it doesn't like the bold inside the header, I think. Command Shift V. What's up with this? Why isn't it, what's going on here? Heading 1, heading 2. Is it just on one side? Oh, okay. Like that. Oh. Oh, so it's space. And then like that. Okay, so now let's see what that looks like. Command Shift V. Aha, this looks sweet. This looks awesome. This is way better than the TXT. Okay, I will go back through chapter 3 and I'll convert this um into this format. This is awesome. Okay, then can we keep the bolds? Command Shift V. It doesn't really do anything. Okay, cool. Let's move on here. That was awesome. Thank you guys for your help. All right, so let's get caught up on some chats here. Theed says, recursion, it's like a donkey running in circles. The program never stops. SSL low toggle mark. Okay, I gotcha. Ustav says, Utstav? How do you pronounce Utsav? Utsav, probably. It was actually star as far as I remember. You need a space after. Yeah, fool me, never mind. AI can make your old notes mark down quick. Okay, that's a good idea. I'll paste it into AI, make AI do it. Okay. We then describe how to perform a formal analysis of the running time of a recursive algorithm, and we discuss some potential pitfalls when defining recursion. Um, oh, this is just the intro. This isn't illustrative examples. Oh, yeah, it is. Okay. Cool. Illustrative examples 4.1, the factorial function. Take all these down. Cool. To demonstrate the mechanics of recursion, we begin with a simple mathematical example of computing the value of the factorial function. The factorial of a positive integer n, denoted as n exclamation mark, is defined as the product of the integers from 1 to n. If n equals 0, then n factorial is defined as 1 by convention. More formally, for any integer n greater than 0. So for factorial 1, it would just be, 1, it's just every number up to n multiplied by each other, summed together, right? Or not summed together, I mean just multiplied together, okay, right? The factorial function is important because it is known to equal the number of ways in which n distinct items can be arranged in a sequence. That is the number of permutations of n items, right? If you guys remember, if I'm any like statistics course, when we talk about factorials, we often talk about permutations, and this is given the example of a deck of cards. Is you can shuffle a deck of cards and it'll be a random order, right? Well, the amount of random orders that you can make with a deck of cards is just 52 factorial. The amount of cards, 52 factorial. So that's just the determining the amount of order or random orders that you can make in this sequence of a deck of cards. I think something is like the amount of deck of cards, like what is it that you could spend like the next trillion years shuffling a deck of cards and you wouldn't get the same shuffle twice or something like that? It's some crazy stat that someone figured out. I don't know. Okay. For example, the three characters A, B, and C can be arranged in 3 factorial, 3 times 2 times 1 equals 6 ways: ABC, ACB, BAC, BCA, CAB, and CBA. There is a natural recursive definition for the factorial function. To see this, observe that 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 5 times 4 factorial. More generally, for a positive integer n, we can define n factorial to be n times n minus 1 factorial. This recursive definition can be formalized as n factorial is equal to 1 n times n minus 1 factorial. This definition is typically, if n equals 0, it's 1. If n is greater than or equal to 1, it's this factorial. Gotcha. This definition is typical of many recursive definitions. First, it contains one of the more base cases, which are defined non-recursively in terms of fixed quantities. In the case n equals 0 is the base case. It also contains one or more recursive cases, which are defined by appealing to the definition of the function being defined. A recursive implementation of the factorial function. Recursion is not just a mathematical notation. We can use recursion to design a Python implementation of a factorial function, as shown in code fragment 4.1. So we have factorial n. If n equals 0, we just return 1, just like our definition up above, right? If n equals 0, we return if n equals 0, we return the value 1. Else, we return n times, we call factorial again on n minus 1. So this is the recursive step happening right here, is calling the same function within itself. This function does not use any explicit loops. Repetition is provided by the repeated recursive invocations of the function. There is no circularity in this definition because each time the function is invoked, its argument is smaller by 1, and when a base case is reached, no further recursive calls are made. We illustrate the execution of a recursive function using the recursion trace. Each entry of the trace corresponds to a recursive call. Each new recursive function call is indicated by a downward arrow to a new invocation. When the function returns, an arrow showing this return is drawn, and the return value may be indicated alongside this arrow. An example of such a trace for the factorial function is shown in figure 4.1. So, right, we start off with the factorial 4. We return, we're starting with call for a factorial 5. So we do 5, and then we do times, return 4 times 6, returns 3 times 2, returns 2 times 1, returns 1 times 1, returns 1. Okay. A recursion trace closely, so if I go back up to my function, return n times factorial n minus 1. So it's going to return 4 factorial of n minus 1. So where does this 6 come from? Return 1, 2, 6. Okay. So let's go ahead and continue on here. Okay. Factorial of 3 is 6. Yeah. And it would return all of these values, right? Here. And then you'd multiply them by 5 each time. Yeah. Interesting. Okay. Okay. Factorial of 3 is 6. Yeah. Okay. A recursion trace closely mirrors the programming language execution of the recursion. In Python, each time a function, recursion or otherwise, is called, a structure known as an activation record or frame is created to store information about the progress of that invocation of the function. This activation record includes a namespace for storing the function's call parameters and local variables, and information about which command in the body of the function is currently executing. When the execution of a function leads to a nested function call, the execution of the former call is suspended, and its activation record stores the place in the source code at which the flow of control should be continued upon return of the nested call. This process is used both in standard case of one function calling a different function, or in the recursive case in which a function invokes itself. The key point is that there is a different activation record for each active call. Got you. So drawing, okay, so that was factorials. This is where it gets hard. Remember factorial n minus 1. So 4 minus 1 equals 3. Factorial of 3 would be 6. Oh, got you. So we were turning factorial of, in this first step, we're doing factorial of 4 so factorial of 5 goes through, and we do 5 times the factorial of 4. Then we do 5 times, oh no, that just gives you one answer back. So then it loops through here because recursion itself is looping, right? There's a loop going on right here. And so it returns 4 times 6 equals 24. Return 4 times 6, which would be 4. Oh, okay, so this is just showing if we did factorial 4, it would run 4 times factorial of n minus 1, which would be 6. Then if we did factorial of 3, okay, so this is like not, this isn't showing the, oh, it is for 5, right? Okay, cool. Okay, so let's go ahead, and before we move on to the next one, let's go ahead and get some definitions in here. We have permutations. Thanks you, Angela, for stopping in. I appreciate you joining me. I'll see you tomorrow. Have a good night. So why am I not getting stuff here? What's going on? It doesn't like that. Oh, it does take it. Okay. Okay, permutations is going to be is the number of permutations. The number of ways n distinct items can be arranged in a sequence. Right? And then we have the recursive definition, right? And this is going to take in, can be formalized as the following. N factorial is equal to 1 if n is equal to 0, and then we'll say n times n minus 1 factorial if n is greater than or equal to 1. Right. That is that. So if we go ahead and do, what does that look like? We'll do it like that. Okay, cool. That's fine formatting for that. And then we got we have the base cases. These are the actually these are more definitions, right? So I should probably put these into the definitions section. So I'll do that. Take these, put it up here, permutations, get rid of that. Take this guy. We'll keep the recursive definitions here, but we'll take base cases and put it above. So the base cases are the definition is typical of many recursive definitions. First, it contains one or more base cases, which are defined non-recursively in terms of fixed quantities. So let's look up define base cases in for recursive functions. In recursive functions, base cases are the conditions under which recursion stops. They serve as simplest instances of the problem that can be solved directly without further recursion. Without further recursion. Perfect. That's a great definition. I'll take that. Boom. Right there. So, cool. Hey, Vance, I appreciate you joining in. Thanks for stopping in this evening. It's good to hear from you. How you doing? Okay. It also contains one or more recursive cases. So the so how would I want to format this? It also contains one or more recursive cases, which are defined by appealing to the definition of the function being defined. So now define recursive cases. A recursive function, the recursive case is the part of the function, the part where the function calls itself with a smaller or simpler version of the original problem. Yeah, so the recursive case is, if it's not the base case yet, we still have yet to get to the base case, we're in a recursive case. If it still can be recurred upon. Reoccurred upon, right? So I'm going to take this code line here. So how can I'm going to take this, I'm going to copy it in Agility. I'm going to say format this in Markdown. Okay, here we go. Copy this, and we'll paste this right here. like so. So now if we go Shift Command V, what does that give us? Cool, it gives us this whole block of code now. So then how do I have to, do I have to close the block? You can wrap the code block in triple backticks. Okay. Shift, no, Command. Oh, I don't have, the backtick is overridden on my keyboard. That should do it, right? No, that didn't work. How do I close it? Like this? Like that? No? Whoops. Anyone know why this wouldn't work? Do I have to put it at the bottom, down here? Like, oh, maybe like that. Shift Command V. Ah, cool. Yeah, we had to close it on a new line. So now that gives us this. So I'll close this bracket for now and I'll open up another one and say and or right. Cool. Like that. Now if we use Command V, oh, that just brings it on one line, doesn't do anything. Whatever. All right, cool. Yeah, this markdown is way better than the TXT. I can, throw in code and everything. I know I did a markdown for the task tracker, but honestly, AI helped me out with that quite a bit. So this is great. Thank you guys for suggesting this. This is a lot better for like viewing for the notes. Like, look how much more simple you can follow this than just a raw TXT file. Like, this is so great. Vance said, finished my first final, object-oriented programming, out of 4 finals. I think I did decent even to get an A in the class. Took a break from studying for my computer architecture and organization final. You are grinding it, man. Good luck to you. You are good. I applaud you, and honestly, I'm a little jealous that you're learning all these cool concepts. So, good for you, man. Pure memorization should be light work. Yeah, I am the opposite. I am really bad at memorizing things. Like, I forget things really easy. It's just normal things throughout my day. I'm very forgetful. So that's why I have to really grind these concepts. um, Samir, I thank you for joining. He says, how long have you been learning Python for? Yeah, I started learning Python at the end of May, beginning of June of 2024. I did it very part-time over the summer, taking my first course of Python CS50P, or CS50P rather, through Harvard online. And then I've just been independently studying on my own and through various resources, such as the Python Crash Course book. We read this live on the channel and completed the Try It Yourself problems live. We are currently doing the Data Structures and Algorithms in Python PDF right now. This is a collegiate level textbook going over DSA and algorithm, or DSA and Python specifically. And then we have Fluent Python that we'll be getting to. And then we have Python machine learning that we'll be getting to. So we have a lot of material we are going to be covering in the next few short weeks to months. So thank you so much for joining, and follow along if that sounds like something interesting to you. All right. How could I? What if I go like this? Screenshot. Let me capture. I'm gonna try to take this right here. I'll capture this. Now, how can I put this in my code? So I'll go file. We'll go save, downloads, save, replace. Okay, that got rid of that. Now I need to drop that into my program here, or into my file, right? Hey Gina, thank you. I appreciate you coming in and saying hello. How are you doing? Vance says the organization class sucks though. The professor doesn't really teach. He just hands us crazy long readings and just expects us to learn it. That's why I'm lucky it's memorization. Yeah, that's really frustrating, especially when you're paying top dollar for this education, when you're just really learning it out of a book, right? You're paying for these professors and their expertise. So, honestly, if that were me, I would, I might go full Karen and complain because at that point, if you're not actually providing any verbal input from the professor and their expertise in the field, if you're learning it solely out of a book, then what's the point of the professor even being paid for it, right? Image path. So we will copy this path, and then we'll take this and we'll say um, we'll put this here as Rawith gave us the text. He said exclamation mark uh, alt text. Oh, alt text as in like do you have to do a quote? Images in Markdown. No. Okay, this is a. We'll copy this. And then we'll go and put the path here. Copy path. Put it here. So now if I go Command Shift V, no, that didn't work. And we might, because we have this. That did not work either. Square brackets for alt text. Okay. You can use relative path. Okay. Oh, let's go like, hold on. I'll just copy the relative path from here. We'll rename this to a recursion trace. Okay, and then we will copy relative path and paste that here. And then if we Command Shift V, that did not get us it either. Let's take it and give it the almighty orb here. Uh, Copy. Let's take it. Whatever. Oh, it just didn't like. Oh, it's not parentheses, it's bracket. Okay, got you. It's not parenthesis, bracket within parentheses, it's just bracket. So now if we do Command Shift V in view, we don't get it. I think it's the path is screwed up. Okay, that didn't work. So what's going on with our path? Chapter 4. Ugh. Okay, let's just go like this. Go dot. Like that. Command Shift V. Cool. There we go. Awesome. Okay, great. So now we have this factorial recursion trace actually being displayed in our markdown here. Awesome. So now let's go ahead and go back to our notes. Get rid of the preview. Let's get rid of all this stuff. We don't need all of these. I got 34 problems up here I can get rid of. Get out of here. Get out of here. Okay. All right, let's get caught up on the chat here. We got some chats. Jeremy says, remove parentheses from around the alt text. Gotcha. Thank you so much, Jeremy. Vance said, the only good professor I had was a dean from engineering at one point. Super nice and humble and taught us importance of tech ethics and other moral stuff. When I was a undergraduate teaching fellow for the general chemistry department in college. I administered a lot of the exam prep and then some just basic study sessions and then also like the recitations and things like that. I had to do a lot of prep and a lot of creating my own problems and things like that, practice problems and things like stuff. But I tried my best to convey all of the necessary material without sugarcoating things, without. I was blunt. Like I would say, I wouldn't tell students like all that. Oh, it might be. I would say you need to know this. This is an example it's going to look very similar to one you're going to see. I just thought that why would you steer people in a direction that wouldn't set them up for success and make things harder? Like why would you make them guess what things are going to be on the exam when um, you could rather than you could set them up for actual success and provide them the things that they would need and give them confidence. So that was my thinking with it. So, but then I was the undergraduate. I was also then my senior year I transitioned. I did the undergraduate teaching fellow, but I also took on a job as the normally they only let graduate students administer and run the actual laboratories for the undergraduates, but my senior year I went to the laboratory instructor professor for the chemistry department. I was like, I want the job. I already was a teaching fellow. I want to teach in the lab now, and so I was able to work as the only like senior undergrad with the graduates and run those labs. And so I was very like while we were doing this stuff in the lab, I would be up on the whiteboard too, like showing practice problems of what was going on in the lab and how it was going to apply to like their exams. So I really felt like I did my best to try to set those students up for success. No, hope not everyone is like me, unfortunately, in that regard. Pretty lessons, to be honest, because once you drift into network programming, ethics comes into play very quickly. Pretty important lessons. Oh, I've never really thought about that. I wonder, like, obviously, Uncle Bob, if you've ever like listened to some of his TED Talks and lectures, he talks a lot about the ethics in programming and maintaining proper clean code and whatnot to preserve the ethics of programming. in the eyes of like government and stuff like that. Uh, and so I would be very interested to join like a more philosophical course on programming and how it affects those aspects, and also like like what you say, Dan Coroner, um, or Dan Coroner. Is it Dan Coroner? And I've been saying Dan Coroner the whole time. Oh boy, I think you're. I think it's Dan Coroner, and I've been saying Dank Coroner the whole time. That is so terrible. I'm sorry, man. If your name's Dan, I'm really sorry. I read Dank. Okay. And thank you so for joining back. I appreciate you coming back. It's good to hear from you again. Oh, it's. Oh, okay. Um, Vance says, I was originally to go into cybersecurity, but I've found just making random stuff and acting like a software guy is fun. Vance also says, I have an offer to join a club as a UI/UX over winter break and help them with website design for the hackathon. I think I'll accept. That's a great offer. You should totally do that. I've seen some people on social media talk about their hackathons, and they sound very interesting. And I wonder what kind of level you'd have to be to join one. If you could also join one, as an already graduate outside of school, if you could join one as a beginner. I'd feel kind of daunting being on a team with really advanced people. I'm like, oh, I'll write the addition some sort of function that doesn't do anything really. My buddy knew the director for the club, so he will let me know. Awesome. That sounds great. By the way, you can also use HTML image tags in Markdown to control the size. Oh, okay, cool. I didn't know you could do that. So I kind of want to do that then. Okay, let's take this and let's do that. So now if I Shift Command V, how do you? Uh, SSLORL. How could you? So what I have to do actually to edit this. So um, can I use HTML tag? Width equals 500. All right, let's take it. No, that didn't work either. All right, I'll wait for your response, but we have that in there now. So if we just see the preview, all right, cool guys. So instead of doing TXT for those that are just joining from chapter 3, like we did for chapter 3 notes, all on Big O notation and introducing the 7 functions for time complexity in Big O. Chapter 4, we were recommended to use Markdown, and so now we're actually having this really cool formatting going on, um, which is really great and more readable. All right. Noe says, "Hey man, where'd you get this PDF from?" This is just the PDF form of the book Data Structures and Algorithms in Python. You can either Google this online to get access to it, or I also have a Discord link below where I have just conglomerated or compiled all of my study resources I'm currently using on the stream and on the channel into one area. So feel free to join the Discord below if you want to see all those PDFs and all my personal notes and things like that. Um, yeah, and then um, yeah, so this one is just DSA in Python, data structures and algorithms in Python. And right now we just finished up chapter 3 and we're moving on right now. We just started chapter 4 today. So we are introduced to recursion here. We've got a recursion trace, which is a visual representation for what's going on within the recursion loop. Um, and so yeah, and then we are going to now move on to drawing an English ruler. But I was just kind of formatting and messing around with the markdown here, trying to get this image to work with tags. um, Parv says this is not how you learn DSA. You're unfortunately wasting your time. Well, shoot. I guess we're wasting our time having fun and doing a hobby. So take me to jail. Take me to jail for wasting my time at having a hobby. Anyways, I thank you though for joining. I'm just reading this book out loud and taking notes, solving the practice problems at the end of the chapters, and then applying all these concepts into my own personal projects, which I work on at the end of my streams, or more specifically on the weekends when I have a lot more time after my 9 to 5 job. For those that are new, I have a degree in human biology, a minor in chemistry, and I work as a formulation chemist for a biotech company. Um, and I'm trying to teach myself computer programming after work and stream my progress for you guys to follow along and just to have a hobby and gain additional skills and further improve upon myself. You might have to switch from single quotes to double quotes in the path. So that does take us to the right. Either do that. No, that doesn't work either. That doesn't work. It's not working. Path is right. Recursion trace. Oh well. Oh well, we'll just leave it, I guess, and we'll figure it out later. All right. Ralphie Code says, W, thanks so much for joining and leaving a comment. I appreciate you. Vance says, I got to get back to studying for the final. You keep grinding. You can join hackathons even after graduating. Just check requirements. Lots of beginner ones, too. Oh, cool. I'll have to maybe look at that and maybe document my progress and do a stream or something. That'd be cool, maybe. But, all right. Let's continue here for another about 15 minutes, you guys, until about 9:30, and then we'll sign off for today. And then come back tomorrow, same time, and I'll see you then. And then this weekend we'll go for a lot longer. But let's get into it. Dude, you are so nerd. Can you make a video on how to become one? Just love it. I need that discipline. I've just been working on my mindset it's kind of cringy, but my mindset over the past few years since I graduated is trying to, shift from that, okay, I'm out of school now, I don't have to learn anymore, to, wait, no, I'm out of school, it's on me to learn now. Okay, so 4.12, drawing an English ruler. So we have this guy right here that we're going to bring back up. Cool. Number 2, drawing an English ruler. So in the case of computing a factorial, there is no compelling reason for preferring recursion over a direct iteration with a loop. In the case of computing a factorial, there's no compelling reason for preferring recursion over a direct iteration with a loop. As a more complex example of the use of recursion, consider how to draw the markings on a typical English ruler. For each inch, we place a tick with a numeric label. We denote the tick of the length of the tick, designating a whole inch as the major tick length. Between the marks for a whole inch, the ruler contains a series of minor ticks, placed at intervals of half inch, fourth inch, and so on. As the size of the intervals decrease by half, the tick lengths decrease by 1. Figure 4.2 demonstrates several such rulers. All right, so we have our largest values, which have smaller values within, which are halves, which are quarters, and so on and so forth. Or halves, sorry, quarters, eighths, things like that. A recursive approach to drawing a ruler. The English ruler pattern is a simple example of a fractal. That is a shape that has a self-recursive structure at various levels of magnification. Okay, we have a definition here. So we have fractal. is a shape that has a self-recursive structure at various levels of magnification. So like a snowflake would be a fractal, right? Or a snow shape would have a fractal. Consider a rule that consider the rule with major tick length 5 shown in figure 4.2b. So this is a letter B here, the middle one. Ignoring the lines containing 0 and 1, let's consider how to draw the sequence of ticks lying between these lines. The central tick at ½ inch has length 4. Observe the two patterns of ticks above and below the central tick are identical, and each has a central tick on length 3. Right, so our halves have a length 3, our quarters 2, and our eighths 1. And our wholes have a length 5. Whole, half, quarter, eighth, 16th, right? In general, the interval with the central tick length of L greater than 1 is composed of an interval with a central tick length L minus 1, a single tick of L, and an interval with a central tick length of L minus 1. Okay, so this is interesting. So what they're doing is consider the rule with major tick length 5 shown in, okay, so this one right here, right? Major tick length 5. Ignoring the lines containing 0 and 1, let's consider how to draw the sequence of ticks lying between these lines. The central tick at ½ inch has a length 4, right here. Observe that the two patterns of the ticks above and below the central tick are identical and have a central tick length of 3. So we have 4, we have a 3, we have a 3. In general, an interval with a tick length of big L greater than or equal to 1 is composed of, so if you have a tick length greater than or equal to 1, an interval with a central tick length of L minus 1, a single tick, okay, gotcha. Although it is possible to draw such a ruler using an iterative process, the task is considerably easier to accomplish with recursion. Our implementation consists of 3 functions, as shown in code fragment 4.2. The main function, draw ruler, manages the construction of the entire ruler. Its arguments specify the total number of inches in the ruler and the major tick length. The utility function, draw line, draws a single tick with a specified number of dashes and an optional string label that is printed after the tick. So we have draw line, which takes in a tick length and a label, which by default has none or blank string. So we have a line is equal to, our line is equal to our tick, individual tick times our tick length that we provide. If the label, we add a label, okay? So this actually just draws the line depending on a length provided with a label. We have draw interval when we takes in the center length. If center length is greater than 0, draw interval, center length minus 1, draw interval. Okay, so this is where a recursion happens right here. So when we draw an interval and we take in the center length, so if the center length in this case is 4, if center length is greater than 0, which it is, it's 4, we draw an interval for center length, which would be 4 minus 1 for 3. And you would do this all the way down until you get to the base case of 0, right? Or 1 tick. So you have 4 ticks. So draw interval would draw all of the ticks of the 3, 2, and 1. You would draw center length. Okay, yeah, this is really, it's confusing, but I'm kind of following along with what it's saying. Okay. Uh, the interesting work is done by the recursive draw interval function. This function draws the sequence of minor ticks within some interval based upon the length of the interval's central tick. We rely on the intuition shown at the top of this page and with a base case of when L is equal to 0, that draws nothing. For a tick length greater than or equal to 1, the first and last steps are performed by recursively draw interval L minus 1. The middle line is performed by calling the function draw line L. So it's going to create a center line, draw a line for the center line, for the center length. So it's going to create this one, and then it's going to create these intervals right here. So if it's 4, it'll create a 3, a 2, and a 1, and then a 0. Interesting. Rohit says, I live here on the East Coast. It's close to 12:30 now. LOL. Yeah, that's what's tough about me being on the West Coast is that I get off work and I start streaming at 7. So a lot of the East Coast people, I feel like maybe miss out on the stream. So that's why I try to do the weekends a little bit earlier so maybe we can get more East Coast friends. Oh, you had to remove chapter 4 from the relative path because you've already in that directory. Oh, got you. So I'll say convert this to HTML for Markdown. Convert to HTML. Okay, so now if I replace it with this, what happens? I do not get the function, the call. That pulls it up. That does not. That does not. Yeah, I can't get this HTML line to work in here. I'm not sure what I'm doing wrong. But yeah, it's just not working. I don't know. Wait, what happened to my notes? Okay, there we go. Some like dash dot image. Okay, let's try that. Not that important. All right, yeah, let's just move on. I feel like it's all right. Whatever. Okay. Yeah, so this is definitely confusing. So, like I said, guys, this is just day one with recursion. So, It's going to be confusing today, but tomorrow it'll be a little easier. The day after that it'll be a little bit easier, and so on and so on. And we're going to get it. So just stay with it. Okay. So illustrating ruler drawing using a recursion trace. Okay, so this is going to be a lot easier. The execution of the recursion draw interval function can be visualized using a recursion trace. The trace for the draw interval is more complicated than in the factorial example. However, because each instance makes two recursive calls, to illustrate this, we will show the recursion trace in a form of that is reminiscent of an outline for a document. Okay, so we draw interval with 3, which draws interval of 2, which draws interval of 1, which draws interval of 0, we draw line 1. So we call draw interval of 3, right? With a center length of 3. When this calls, it runs draw interval of 2, which recursive downs to draw interval of 1, which then prints the single line, because we can't, this is our base case of 0, right? Then it runs this draw line center length right here at 2, and then we repeat this same process again for draw interval 2 here. But we do a draw line 3 here though. Draw a line on center length 3. We draw interval 2. Sorry if my camera's covering this up. It's kind of difficult to show it all. But so we have this draw interval function, which takes in some length, center length. So in this case, it takes in draw interval 3, right? We go through and we draw interval of 3. If center length is greater than 0, which it is, we're going to go ahead and do these 3 things. We're going to recurse through for 3 minus 1 every single time. So this becomes draw interval 2, draw interval 1, and draw interval 0. So if draw interval is greater, now this becomes, if it is 0, do nothing. Draw a line. Oh, because you're calling all of these in every recursion. I was thinking you're just recursing reoccurring this one line or whatever. But you're calling, every time you run this recursion, you run it for all 3 of these for that specific instance, and then you're calling it again here. So all 3 gets ran again for that recursion. So you have a sandwich going on between. So these will be the same recursions going on, right? Which is shown here. So we have draw line 2, interval 2. This is our center line right here. Draw line 3, which is this. Two, 1, 0, 1, 0, 2, 1. Yeah, this is definitely tricky. All right, you guys, it is 9:30 today. Let's quickly open up the small business manager and just see what kind of progress we made on this last time and give a quick overview of what this is for any new people. It feels like the base case would break you out of the function, but the previous recursive call, quote, unwind after the base case is hit. Recursion algorithms are always hard to wrap my head around. Yeah, definitely. I'm feeling that for sure, but we'll get it. We will get it. Don't worry, guys. So I just want to quickly, before I sign off for today, go over the project that we're working on for anybody that is new here. At the end of my streams, if I have some time, I know today we jumped into chapter 4 and we got really into setting up the markdown and everything. So I kind of got tied away and busy with that and learning new material. But I often like to actually implement and practice that learning and practice coding because you actually need to code rather than just keep reading out of a book. So I've created some projects that we can hopefully implement this learning into. So right now we have a small business manager project, and what this project does is a one-stop shop for a small business to manage their inventory, potentially down the road their expenses, manage their sales, transacting that inventory into sales, um, developing income statements, tax documents, and all that kind of alike. So a kind of one-stop area. Think of like almost like TurboTax, but you can maybe like insert it manages your inventory as well, and then creates your documentation based off of your actual environment that you have loaded in. So right, we have a just a class file here which just handles the inventory. So we have the item class, which is the kind of our base class here, where items are created and loaded into the system with under this identity of an object-oriented item class. Those items can then be converted into for sale items when they are listed for sale with additional parameters such as a price and a date listed. And then those items can be converted into sold items, which take on a sold price and a date sold. We also have a mode class, which is still in development. This is very rough. I kind of threw this together really fast, but this just takes in the sold item. It supers or carries over that item number as a tracking mechanism, right? We're not creating new items. We're just attaching a class, in this case mode, to the item, which just tracks the overall um, movement of the item from purchase to customer, like either shipping or delivery, or and then tracks those attributes like price and things like that for shipping and costs. So uh, yeah, so that's kind of that. And so then we have our actual program here, which we have our top half of our program is called our process functions. And these actually are kind of are like the flow. These are the menus that are created that are the users interacting with the overall structure of the program and script. But then we have our operational functions, which just actually do the work behind the scenes for the structure built within through the flow functions or process functions. So just to show you an example of what's going on here is if I run the program, it looks very similar to my task tracker. I kind of have a theme that I stick with for right now. I would like to hopefully get into UI, GUI development using maybe Tkinter or PyQt down the line in a version 2.0. But I think just for now, let's stay in a CLI, a terminal environment, and get something actually working, and then we can transition it into a 2.0 version with a desktop interface. So if you're interested in that, follow along. But let's go ahead and open up the program. This just has menus for inventories and transactions so far. So we will maybe add another thing for like expenses, so on and so forth, maybe like documentation, well, yada, yada, yada. So we'll have, we can, right now we don't have anything for transactions, but if we press 1 for inventory, we can actually add items. So we have successfully added these two functions. So the add item and the find edit item function are implemented, not in their full, but they do a general job right now. So our add item function, just, like it says, will just prompt you for questions regarding your item, take that information, create those item objects, and then load them into the system. Now, we also added a feature where you can bulk add with a quantity. So before we had a quantity for items being associated as instance variables or these attributes, and we decided that was against the definition of an item as a whole, because an item is a singular item level. It is a base item, whereas having a quantity would cause it to become a not singular but plural or multiple in a sense. So we took the quantity and put it outside of the class and just made it a factor that you can multiply and duplicate the creation of a single item. So if we go ahead and press 1 add item, make this dress, right? cost was 10, item size is medium, today's date. We also added this, right? So we can say no here rather than using today's date, and then we can put in a custom date like in the past as if we forgot to upload this item. So it'd be like 2024, 12, 1. And then let's say, so right here now we're prompted with a quantity. So if you press 5, this just duplicates that item for 5 instances. Um, each with a unique item number is key, right? So we track items with their item number. So if I go main menu and then just quit the program so things save, you'll see in my items class those dresses were created 1, 2, 3, 4, 5 objects of duplicate with incrementing item numbers. So that is successful in that. Um, Now, like I said, we could just press 1 on that to use the current date instead of a past date or whatever, but we successfully are able to create these custom dates as well, which is cool. We added that last time. Now, if we enter the program one more time, go to inventory. Now, we added the find edit item. Now, we added in the item number search parameter here so far. So if I press 1 here, we have to provide an item number. If I say 100, error, item not found, item number equal 100. So then we're prompted with a new item number. So let's say 80. Oh, we don't have 80. Let's say 70. Oh, we don't have 70, 60. Let's go all the way down to 40. Let's go 20. Oh, we found an item number 20. And there it is. So we do need to add an option here to actually exit out of this loop. We're stuck here currently. So we will work on that tomorrow. We got stopped prematurely before we could finish this function in its entirety. But we do have a good structure for how we're like accessing these items. And you might be asking, how are we going to implement the learning, and how are we going to what are we learning the data structures and algorithms for? Like, why are we doing that? Well, if you think about it, the users in this case, whoever is using this program, will be loading items into their system, and this specific business could have upwards of 1 million, 2 million, a quadrillion items, right? They could have a ton of items that they have loaded into their system. And so we need to be able to have, binary search algorithms. We need to be able to have all these sort of algorithms needed to properly and efficiently run in probably like either linear, logarithmic, or some sort of efficient time manner to access these items within our database. So we are going to be implementing the algorithms that we're learning into this function when we get there. So obviously we're not there yet in terms of our knowledge. We're just getting into it and getting our feet wet right now. But when we get into the chapter and get into actually learning about those types of algorithms and how to write them, we're gonna put this right on into our program. So it's gonna, and then we're gonna keep adding features, add expenses, add ways to track expenses, use the sales minus the expenses with filter parameters to print and generate reports for various months, days, years, whatever kind of. It's really limited, like I say, to our own creativity and willingness to work and try to just do stuff. So I like to ramble and go on, but if that's something that you're interested in, then this is the place for you. And we're going to be working on this. This is my hobby, and I really enjoy doing this and enjoy doing these streams and documenting it all. So yeah. Jordan Wood says, how did you get your terminal to look so clean? Mine always shows the execution path. Right now, it is just because it's running right now. I have a function here called clear terminal, and this I have placed at specific points within my program to actually clear that terminal, like either before loops or maybe inside of loops if I want to clear. Now, I have to be kind of selective about where I put this because I don't want to wipe all the information out if I need that information, especially while looping, right? If I just wipe it and then I continue through a loop that I haven't restarted, then I kind of, the user might get lost. So I have to be careful about where I put these. But I have this clear terminal function, which is just this right here, where it says its OS name is NT, we clear, else do this clear, which this is for Windows users, I believe. And I just call this function at various points to actually reset and just blank it out. But that's why it's clean right now. But if I were to just exit out of this and run like here. As you can see, you have my file path here associated with my terminal command. So it's there. It's just while my program's actually running, it's not going to display this prompt because you're not getting any. You're not continually prompting um, or getting a an argv argument from the CLI here. A dig says, can't you just have like one item class and some enum for its status sold and on sale? Yeah, so I thought about that. Like we could have a like a switch indicator to indicate that it was sold, or um, you know, like oh, sorry, if it was sold or for sale. That's definitely a way of going about it. I don't think there's anything wrong with doing that. So I don't have any combats to going about it. But I also think that there's not anything really wrong with going about it the way we're doing it as well. In fact, I weighed, I think I actually asked ChatGPT that question. I said, would it be more beneficial to just have one item class and then have some flags to say, okay, if it is sold, this becomes true, and then it gains all these attributes and yada, yada, yada. Um, and it just said, yeah, you can definitely do that. There's nothing wrong with that. And, that's definitely, if you want to go down that path, do it. But also said that you can, break them up into their individual classes and have them inherit from one another just to have things a little bit more organized. Now, like it can just be a little bit more confusing for someone trying to read your code, especially for beginners. Um, if everything is just in one massive block of a class, they might not be able to follow what's going on as easily. And so I also wanted to make this readable for beginners on the stream to follow along. And you can kind of follow the chain of inheritance here pretty easily. And it's pretty intuitive. Like items become for sale, items become sold items. So it makes sense just in terms of like logically speaking and programmatically speaking. So Rolla says, I like what you did so far. I'll try this project, try to implement, and if I make any improvements or optimize anything, I'll make a PR. Now I know what I'll be doing this weekend. Great work. Awesome. You're gonna I'll try this project, try to re-implement, and if I make any improvements or optimize anything, I'll make a PR. A public repository? Is that what you meant? Cool. Well, awesome. Appreciate you stopping in and glad we could help you out, give you some insights here. Rohith, thank you. Yeah, so, and also, I would like to say, right, we also have file writing systems being taken place. So this program, similar to our task tracker, is, saving our file, our class, our objects when we exit and loading those back in. And so when we create new items, it predetermines the item number available from the last item in the list. So we had to be able to read those files and save them. So we actually implemented that as well. I wrote that entire the load and save file functions on stream. They're very long. I could definitely break them up and optimize them into smaller functions that call one another, but I just left it all in one block because I don't know, I got lazy. But so all that's kind of happening in the loading and saving files is that is that right we if it's not we first decide we kind of run an is instance type, right? No, Python has a method called is instance which checks for if a variable or a data inside of a variable is an instance of either a string or an integer or a float, and it returns like a boolean true, yes or no. um, Now we don't have we could maybe make an instance of a certain class, right? But I kind of created my own with this sort of type um, given here. So this variable type, if type is not one of these strings, then we raise this error here. And so these are just my is instances in a sense where I've custom created strings that have our flag indicators for what file to load. So this will, if load file quote items will load the quote items CSV file. If I provide for sale items as the type flag for this function, I load the for sale items file. So, and you'll see that When I press 1 to actually enter the program in this stage here, right, I actually call the load file for that items flag. I call the load file for the for sale items flag, and I call the load file for the sold items flag. And all of these load file functions return a list of all of the files or the items already existing in the file. And so those lists just get appended or get saved as the values associated to these keys, right? Stay with me here. This is getting pretty in depth, but the returned list of items already found in the file, quote, sold items, for sale items, and items, are saved to their associated, dictionary key in the all items dictionary, which is up here at the top of our program. So that's kind of the data structure. That's how that's being managed. And now I don't really know anything really about data structures, and we haven't got there yet for in the book. So right now I'm just managing the inventory like this. So we'll see if there's anything else we can do to optimize that further. Um, Anything else here I can quickly jot over before I sign off for today, and we can come back tomorrow and work on a lot of these features. Mm, right, so we have the find edit function. Right now we only are able to find by item number, but we're going to add in a find by name and a find by date created feature, just to add more user friendliness and modulation. Um, I will also note that um, we are dealing with monetary values or currency in the terms of integers in cents, right? We're not in dollars and we're not in floats because we understand that floats can interact differently on various other machines, and they can also round incorrectly in some cases. So what we're doing is when a user provides a monetary or currency, if the user provides it in a dollars dot cents format, 12.25 or $12.25. We detect the period, we split on the period, we save dollars, we save cents, we convert the dollars to cents, and we add the two together as total cents. And then the same thing happens if you just provide cents. Well, then we just do nothing and just combine. If you just provide a whole dollar, well, then I have a detection for doing that. So like I think it was in the add item here, we have a price right here. So we try to get a cost from the user. So we need to account for strings of quote 250 or 20 as well. We need to account for periods being given. We need to account for whole dollars. So we did all that. So if the period, we split on the period, we convert those to integers from strings, and then we concatenate and convert dollars to cents and combine our cents for total cost. Um, Else, right, if the user just enters in a whole integer value, we try to convert that and just run and do the conversion from dollars to cents on it. Um, right, else meaning except for a value error, meaning that we got an option that wasn't provided. We have these associated catches right here that will, you know, uh, monitor our inputs. Cool. Um, Anything else I can say? No, I think that is gonna do it for me today, guys. It's almost 10 o'clock here. I've been going for 2 hours and 30 minutes. Like I said, I stream every single day almost, or at least I have been for the past like 2 weeks. Been really, really motivated to learn, and the stream has been growing and also motivating me. So I can't thank you guys enough for participating and joining along, making this much more enjoyable and just much more of a fun environment as a whole. Um, I'll see you guys tomorrow where we will continue with chapter 4 of data structures and algorithms in Python, and we will set some time because tomorrow's Friday. I don't have to work on Saturdays, so we can do a late night stream if we wanted to, and stream until the AMs if I can stay awake, and we can work on adding some more features for this project and do a late night grind and maybe make it more fun, have some like cool like we can watch some videos or something, make it maybe more fun rather than just uh, learning for a long time. Um, but yes, everybody, yes. So I'll see you guys later. Harry, thanks so much for stopping in. SS Low, Avinash, Rohit, A Dig, Jordan Woods, everybody, Jeremy, Yusa, Ralphie Code, Vanch, Parv, Gina, Dank, Ron, Dan or Dank, everybody else, Samir, uh, Dat Kid, uh, Kerwin, you guys have been awesome. Thanks so much for joining the chat and the stream today as well. Guys, I also posted a video to my channel today for which goes over and demos the Task Tracker project. Um, and so if you're interested in seeing the Task Tracker project that we built live on stream when we were going over the Python crash course and everything, feel free to check that out. That is up currently. That obviously utilized a lot of more basic beginner Python functionality using Python Crash Course, and it helped solidify all of that learning into one more major project where it saved files, read files, had a third-party package installed, used virtual environments, lists, everything. So it just really the task tracker put all of our learning into one place and showcased that we actually read this book and were able to make something with it. So yeah, we're making great progress here. I'm super ecstatic about how we are improving, and I'll see you guys tomorrow.